Today is Majid Khadiv. He's one of the organizers of the workshop. Majid did his postdoctoral research in movement generation and control group at MPI for intelligent system. During his PhD, he participated in Surena 3 humanoid robot project as a lead control developer. He also spent 1 year of his PhD as a research visitor at the Autonomous Motion Department at MPI. His main research interest is control of robotic systems, especially rugged robots. With Majid, the stage is yours. We are looking to hear your presentation.
Thanks a lot, Farbod. And thanks a lot, everyone, for attending my talk. Today, I'm gonna be talking about my recent effort based on model-based control and data-driven control for legged locomotion. So the first question that comes to everybody's mind is that why legged robots? If we have a quick look around ourselves, we quickly can figure out that there are plenty of applications, plenty of jobs out there that are absolutely dangerous for human beings, but at the same time, they require a certain amount of dexterity. So if we have humanoid robots or legged robots with a similar capability as humans, then we can replace humans in these dangerous jobs. The research we do in legged locomotion and the knowledge we gain can be used to design and control exoskeletons and also prosthetics. And finally, we can use humanoid robots to help elderly people, to educate our children, to use them in home care services, and so on and so forth. So with this picture, you can see that there are plenty of applications out there that are waiting for humanoid or other legged robots to become mature enough such that they are used in daily life. The problem is that legged locomotion is extremely hard. First of all, because these robots can make and break contact with different parts of the body, and this renders the control problem very complicated and high dimensional. These robots are inherently unstable, which means that if they are not controlled properly, they can easily fall down. They have a kind of state-based and time-based switches that are essential for these robots to move around. So these robots need to make contact, break contact, such that they can move their center of mass around. They are prone to external disturbances, to environmental uncertainties, to perception uncertainties, and so on and so forth. And finally, these robots, the amount of interaction forces can be highly limited. So it can be properly controlled such that they can move these robots around. And there are many sensors and actuators in the structure of these robots that should be working simultaneously such that these robots do a simple job like standing. So this problem is generally very hard to solve, the control of legged robots. So before I jump into the theory, I would like to say that all the demos I'm going to show is using the robots in Open Dynamic Robots Initiative that are designed by Felix Gerimenger in our lab. We have 2 quadrupeds, Solo 8 and Solo 12. We have 1 biped boat, and we have a 3-finger manipulator for dexterous manipulation. And they all have a similar kind of design concept based on proprioceptive actuation, and they are auto controlled. So here is the OG web page. You can look it up. You can see the open source hardware design and all the components. All of them are based on 3D printed material and off-the-shelf components. So anybody can go there, look at them. If the universities or other institutes are interested, they can just start kind of building their own robots. So now let's jump into the theory, let's say a bit. So if we look at the structure of dynamics of this robot, we can see that there is a continuous part of the dynamics, which means that as long as these robots do not go to a switching surfaces, they have a simple ODE equations, and the control input, which is U here, is highly limited. It should be inside a set. But as soon as they go to a switching surface, it means that the dynamics changes and they can go to a jump in the states if there is an impact. So the whole dynamics is a hybrid dynamical system. If we look at the continuous part of the dynamics, we can split it into 2 parts. One part is the actuated part, which means that we can exert torque in the joint such that we apply forces to the environment, And using these forces based on unactuated part of the dynamics, we can move the center of mass around. So the second part is more interesting and is it kind of needs enough care for controlling these robots. So these dynamics can be captured using centroidal momentum dynamics, which says in order to move the center of mass or change the angular momentum, you need to exert external forces. This dynamics, however, is in general nonlinear, which means that if you want to use this to do optimization, it's going to be a non-convex nonlinear optimization problem. But there are some kind of abstraction of these dynamics here. For instance, it's LIPM, which says if you limit the motion of the center of mass on a certain height and and the rate of angular momentum around center of mass is 0, then you can end up having a linear dynamics, which is very nice because we know how to control linear systems. And this is a kind of block diagram of the control system that we normally use. We are given a desired behavior. For instance, for walking is the desired walking velocity. We do trajectory optimization to optimize trajectory for the most important points of the system, like for instance, center of mass or the end effectors. And this part, if we can solve it very fast and if we can close the loop, we can do it in a closed loop MPC fashion. And then we have a whole body controller that maps these trajectories to the full joint torques. So this is the normal control framework that we use. The first question I would like to talk about in this talk is that how to control walking of different robots. So in this picture, you can see 3 robots that I've been working on during past 5 years. On the right, you can see Hermes. It's a fully actuated robot with many degrees of freedom in the leg, and all of them are actuated. So this helps us to be able to control the interaction forces directly by modulating the torque at the ankle, at the toe, and so on. However, the leg is super bulky, which means that it's heavy. In order to do the dynamics motion, you are very limited. On the left, you can see Bolt, which is a minimal designed robot. It has only 3 actuators per leg, and the foot is a line, which is there only in order to prevent the robot from rotation around Z-axis or normal axis, and the ankle is fully passive. So this robot has a very lightweight leg, which means that you can easily move the legs around, but you cannot directly control the contact forces using ankle joint, for instance. So controlling this robot becomes more challenging. In the middle, you can see a trade-off design. Athena has a locked ankle, I would say, without any actuation, but it has prosthetic fit, which means that it gives you a bit of flexibility at the foot. Here, you can modulate the forces or center of pressure inside the support polygon because you have a support. However, again, you don't have ankle actuation that you can control contact forces directly. The question I would like to answer is that, is there a single walking controller that enables all of these robots to walk robustly? And here, since we want to control the walking motion, we would resort to using LIPM. However, the main intuition here is that in order to control all these robots that have different control authority over the contact forces, we can only control the switching surface. So we can virtually constrain the center of mass to move on a surface. So the continuous part of the control will be gone by, for instance, trying to have the center of mass moving on a constant height and trying to have 0 angular momentum around center of mass. And then the only thing that you can control are step location and time. So based on that, you want to control the walking of this robot. And this is a general strategy that is not dependent on the type of the ankle joint, the type of foot that you have. So I will just very high level say how it works. Very fast, we can find next step location and timing using integration of the current state of the system up to the end of the step. And then we can write down a convex optimization problem such that we select optimal step location and timing given the current state. Then we can find a proper swing foot trajectory for the updated step from the next first step. And finally, we can send these trajectories to, here we use hierarchical inverse dynamics to track these trajectories. A couple of years ago, I implemented this in simulation. Here is the simulation of Athena. Athena doesn't have, again, actuation in ankle. However, here, by only adapting a step location and timing, we are able to control this robot very robustly. So the robot is robust against external pushes, against slippage, I would say, and it can recover from these disturbances. Also, the thing that we showed is that timing adaptation is quite important for humanoid robots. Here in this figure, we show the amount of push the robot could recover from in different directions. And green is our work with timing adaptation. Blue is an LIPM-based MPC with only a step location adaptation without any step timing adaptation. So you can see that by adapting the timing, you can improve a lot the robustness of the gate with respect to external disturbances. So the main idea is that we don't need to control the center of pressure, or we don't need to control the center of mass horizontal component. The only thing that we do is that we would adapt the step location and timing such that we have a desired gate, and we can resist against external disturbances. Also, we showed that with this simple strategy, we can guarantee viability, which is a forward invariance, weak forward invariance, by only looking ahead to the next switching surface, which is the next step. And finally, we can do very fast replanning with both step location and timing adaptation. So the main idea is that we forego controlling this continuous part of the dynamics, and we resort only to using adapting the switching surface, the step location and timing to control working of the robot. So recently we have improved this strategy. This is the work of Elham that we did. And here we added the swing foot dynamics. So I'm not going to go to detail of this work. This is going to be presented next week at ICRA, so you can watch her talk. But here is the experiments we did. So this is both. It's walking forward and backward in this video. And again, there is no control of the horizontal motion of the center of mass. We are only adapting step location and timing to control the walking and to deal with disturbances and uncertainties. So here, actually, the weight of the wire is not negligible. And if you see, sometimes I'm perturbing the robot, but it's adapting its parameters to recover from these disturbances. Here is another experiment on uneven terrain. And the robot doesn't know at all about or the controller doesn't know about the unevenness of the terrain. However, because of the torque control and compliance of the system, and also adapting step location and timing, it's able to recover from all these uncertainties and the kind of environmental disturbances. We also tested the algorithm on a soft terrain. Again, in the controller, we assume that the environment is rigid and the surface is rigid. However, thanks to the robustness of the control, the robot is able to walk on a soft terrain. We did a lot of push recovery experiments, and the robot is stepping in place. It's pushed in different direction, and it's adapting its steps to recover from this push. The other nice thing is that it doesn't only adapt next step, but it can adapt several steps to recover from huge pushes. Also, we did some sagittal pushes. Here you can see. And finally, the interesting part for me, especially, is the slippage recovery, I would say. So the robot is walking on a moving platform, and thanks to adapting step location timing, it's able to recover from all the disturbances by this moving platform. Okay, so Julian, a PhD student in our group, he adapted the same walking controller and tried to control. He just did some minor changes, and he adapted the locomotion, the walking controller on quadruped robot. Here he has access to a joystick, and he's moving around the robot. The environment, again, we have some, let's say, uncertainties. And again, the robot is able to walk properly on this with all these uncertainties. So here, because we have a quadruped, we can also rotate around. Also, I will go a bit forward. Here is some kind of push recovery he did. Okay. So I will also, so those were the work based on the step location timing adjustment. Also, we did some work with Ahmad, a PhD student in our group, and we tried the use of stochastic and robust MPC. So here we have a kind of a state constraint on the path of the robot. The robot wants to move through a doorway. And here it's a safety critical constraint that we have. And with the stochastic MPC, we consider all the uncertainties. And then with the 99% probability of COM constraint satisfaction, we are able to, the robot is able to move through the doorway without colliding with the environment. Robust MPC also can do it. However, this comes at the cost of higher cost, let's say. So MPC is, the cost is very low, which means that it's efficient, but however, it violates sometimes the constraint. Or MPC is very conservative, but it doesn't collide with the environment. SMPC is a trade-off between these two. So Ahmad is going to present this work in humanoid. So if you're interested, you can watch his talk in 2 months, I would say. Also, we did a bit of work on the learning of the step location and on event train. This is the work of Avadesh. Here we did, what Avadesh did is that he trained a Q network, which tells you where to step, given the current state of the system. So here is walking of the robot on different surfaces that are really hard to use optimization for. For instance, these are discrete surfaces, or when we have non-convex surfaces, it's really hard to write down the optimization problem for it. Also, Avadesh is going to present his work next week. So if you're interested, you can watch his talk. Okay, so now how about if we want to have more complicated motion than walking? For instance, if the robot wants to do a backflip, let's say. So here we cannot anymore use LIPM because the center of mass is not constrained to move on a flat surface anymore. So we need to go to the nonlinear, accept the nonlinearity and go for solving the general problem, centroidal momentum dynamics. And we cannot anymore just adapt the switching surfaces. We need to carefully control the contact forces such that they realize the desired motion. So here is the trajectory centroidal dynamics trajectory optimization that we have. So in the cost, we would like to, let's say, track a desired momentum and the desired trajectory of the center of mass. The main constraint is the centroidal momentum dynamics, which is non-convex. We have a second order friction cone constraint and some other constraint. So this is a non-convex nonlinear optimization problem. And thanks to the solver Brian developed in our lab, we can efficiently solve this problem using a sequence of convex approximations of the centroidal dynamics. Once we have a trajectory for the centroidal, we can do a whole body inverse dynamics, inverse kinematics around these trajectories, and we apply the constraints that we have, and then we could iterate between these two solvers such that they come to a consensus in terms of the momentum. And as soon as this consensus is made, we can make sure that we are satisfying force constraint by centroidal dynamics, and we are satisfying whole body constraints using the whole body inverse kinematics, inverse dynamics. So this is the solver. Basically, Alex and Brian have been developing in our lab. And then I started to use this solver and implement some motion from these solvers on the robot. So this is Solo 8 robot. The first thing I did, so the thing that I'm going to show now are only trajectory optimization. There is no MPC. We have we generate the full trajectory, and then we have a low-level controller, a task space impedance control. Here we use to stabilize the system around the trajectory. So here is a very simple slow walk. So this trajectory is predefined, and the robot is only tracking this trajectory. So here is just a proof of concept. We want to show that, okay, we can generate walking motion, and the robot, and by only tracking it, we can have a simple track. And surprisingly, we can have, even with this trajectory optimization, without any replanning, the robot is able to walk on a seesaw with all the, which is unknown, and the robot didn't know about this, the planner didn't know. and it can robustly traverse the surface. And also we had some fast trot here. So here, because we used Vicon and the velocity was a bit noisy, you can see that the base is a bit shaking. But by moving toward IMU, we didn't have any more this problem actually. So now we want to do more complicated and more interesting motions. Here is the jumping. So the robot can jump more than 5 times its body height. So its standing height is around 21 centimeter. And the robot could jump, I think, around more than 1 meter. And here again, we generated the trajectory and we have a local controller to track this trajectory. The thing that is very important in this motion is that we need to change really the impedances or the gains if we want to have this motion. So during push-off, we really need to have very high gains or impedances such that we can exert so much push-off force. However, during landing, we need to have a very low stiffness and high damping, such that we have a proper stabilized landing without any bouncing. Here, what I did was that I just had some gains for push-off, very high gains for push-off, low gains for landing, and in the air, I just interpolated between. But if you want to do this, let's say systematically, this is a new work that Bilal did, and it's very interesting. You can use risk-sensitive optimal control with measurement uncertainty, and you can consider contact uncertainty and have the jumping motion with a proper set of optimal gains that stabilizes the system. So if you are interested in his work, you can, again, he's gonna present his work next week at ICRA. I also did some other motions. Here is a combination of, let's say, quasi-static motions and then a very dynamic motion. Again, it's only a predefined trajectory and a local controller around this trajectory. This is another view of the same motion. So here, we also use the capability of the robot by rotating the hip 1 full turn, which could be very useful for climbing the obstacles. The thing is that we all know that these motions don't work in the first try. So what I would do is that I would sit there, I would generate a motion, run it on the robot, and then look at the data, look at the video of the motion, and then I would decide to change some parameter, which could be some regularization term in the trajectory or some feedback gains. And then at some point, I would have some motions that are working, but each with a different kind of performances. So here, after some, this is only 1 day of trial on this robot. So the idea was that we wanted to jump on an obstacle that has the same height as the robot. And then we needed to do many trial and error to do that. The third question that I would like to answer is related to this. And it's that how could we use this data? How could we do this procedure that I'm doing manually automatically? And this is one other work that we did with Muhammad, a master student in our group. So the idea is that we have a normal control pipeline. We have a kind of planner and a controller. And the idea is that we would close the loop using Bayesian optimization here because we do not have so many parameters to decide. And Bayesian optimization would try to find the optimal cost weights of the high-level planner such that we have a robust motion. So for instance, for walking motion, if we look at the cost function that we have, we can write down a performance term. Here is a velocity tracking term in different directions. We have some robustness term. For instance, for walking, we can have ZMP as close as possible to the center of the foot or center of the support polygon. So it's kind of a robustness term. The third term is that step locations should be as far as possible from boundaries of the reachable area. And finally, we need to have some terminal cost that tries to guarantee or bring the system towards some invariance. And then we have some set of constraints, inequality and equality. So for instance, if we don't have any beta in this equation, which means we do not regularize ZMP, because ZMP is the most important constraint for walking, and most probably the solver will find the solution on the boundary of the foot or support polygon. But as we increase beta, we are pushing the solutions toward the center, which means we will have robustness against this constraint. However, this comes at the cost of degrading the performance or putting other constraints on the boundary. So the question is that how could we find in this equation alpha, beta, delta, and eta, such that we have a best trade-off between performance and robustness? And here is a kind of simulation that we did. So we added many different uncertainties to the simulation. We had a motor model, we added delay of the computation of the MPC and everything. And you can see that at the start, and also we have external pushes during each episode. And in the right, you can see the velocity tracking performance. So at the start, the motion is very robust. However, the velocity tracking is super bad because we want to go forward, the robot is stepping in place. But then the Bayesian optimization is exploring, changing the parameters to find the best trade-off between performance and robustness. And we are randomly disturbing the system with external pushes. So sometimes the robot falls down, sometimes it manages to go forward. And after 13 queries of BO, Bayesian optimization, we could find a solution that was robust against all the disturbances. And if you could see in the right, the velocity tracking is quite good. So the robot goes to a desired walking velocity, and at the end it stops, while it's at each episode we have some random disturbances exerted on the robot. And here is the history of the search by Bayesian optimization. For instance, you can see that after around 13 iteration, it could find already a very good solution, and the rest, the exploration didn't really help so much. So this gives us this intuition that if we do this on the robot, maybe after a certain number of iteration, we can find a robust motion and that achieves the performance that we would like. The other approach that we use with Miroslav, another PhD student in our lab, is to use deep reinforcement learning for controlling legged locomotion. Here is we have a simple hopper. The idea is that we would like to jump as high as possible, and we compare two different policies. One policy that outputs only desired position of the PD controller, and the other outputs with a fixed PD gain, and the other outputs both the desired or desired target for the PD and the gains or impedances. And you can see that both can manage to handle different amount of height uncertainty of the environment, which is really hard in general to handle with the trajectory optimization, because this is very hard problem for contact timing and contact location uncertainty. So you can see the robot seamlessly perform with different disturbances, and we showed that with variable impedance we can have better performance in general. So here the motions we generated, because the system is low dimensional, was from scratch. So DeepRL, we used DDPG here, and it could explore and find a solution that do this task. However, for more dimensional systems, I believe this is not possible. For instance, if you want to do this on the quadruped, we need either an imitation or a demonstration or something. So here, what we did in a new work is that we generated full body trajectories using trajectory optimization. And then what we do is that we would try to cache the solution of the trajectory optimization to a state-based neural network, while we have different type of contact uncertainty in the simulation. And this would end up with a robust policy to the contact uncertainty. This is the block diagram. So in stage one, we are given a demonstration trajectory. We would only try to track this trajectory. And we would have, in end of stage one, we would have a nominal behavior. It's a policy, but this cannot be transferred on the robot. Then in stage two, we will try to add only the task reward and some regularization such that we can transfer these motions on the robot. And the output of this stage is just a policy that we can do directly on the robot without doing any more optimization on the robot or training on the robot. So on top, you can see jumping motion with different type of disturbances. And the bottom, you can see bounding motion with different type of disturbances. And the policies we gained are really robust. So I'm very excited about this work to see how we can extend it for more and more different tasks and for a general problem. So the policy is really robust to different type of contact uncertainty and also external pushes. And it was really hard for us to tackle this problem of contact timing uncertainty with trajectory optimization. But here with the reinforcement learning, we could find some policies that are really robust to this kind of uncertainty. Okay, to wrap up, I would say model-based approaches can generate very efficiently nominal behaviors without any sample. You have a model, you can generate good trajectories for the system. For doing model-based control, I think exploiting the underlying structure is extremely important. If we just pass this, write down the problem and pass it to a solver, I think there is little hope that we can have things working. So we need to really exploit the structure of the problem. I also believe that combining model-based approaches with learning, it can provide us with a fully automatic control pipeline. So this is kind of my dream, that I can have a fully autonomous robot. And I believe for that, we would need a combination of these two. And finally, RL can help us a lot with having policies that are robust to different type of environmental uncertainty and robot uncertainties. So I believe in general that we need to have a combination. I don't know yet what the best combination is, but this is the thing that I would like also in the future to work on. By this, I would like to thank all my collaborators. Without them, I wouldn't have been able to do any of these works. And also, these are my friends in Machines in Motion. And with this, I would like to thank you for listening to me. I think my talk was very short, and I would like to have many discussions, and I have many questions. Thanks.
Thanks a lot, Majid. Okay, now we start with the Q&A session. We have the first question here. So I have some questions regarding the contact robustness. Are your algorithms lifting robust, or will it explore if you lift up the robot, if you fall down, lose contact? I think it's robustness about respect to the lifting.
I didn't get quite.
So if I think what he means is if you lift the robot up,
okay,
does it have a robust behavior?
Yeah. There's no problem here because this is a fully state-based policy. It's not time-based. So if you put the robot in the air, there would be no problem. Actually, we did many tests in terms of dropping the robot from different heights, and the robot could very fast go to the desired behavior. So also you can check the abstract that Miroslav has in the workshop. It's on the webpage, and the algorithm is explained properly there.
And do you switch between the different controllers during the swings and stance lift?
For which part? I'm not sure. So no, it's just one single policy that has all the motions. So there is no switch. Yeah. However, for the
Can you hear me?
Yes.
I mean, how about the inverse dynamics based algorithms, not the policy-based ones?
For the inverse dynamics ones, I think we would need a trajectory, right? So generating trajectory is another part. And then what inverse dynamics can do is that it only can track some desired trajectory. For balancing or for this task, perfect. I think inverse dynamics is perfect. But if we need to do some jumping and very dynamic motions like parkour, we cannot do it based on only inverse dynamics, right? We need to generate some physically consistent trajectories such that inverse dynamics can track that. So inverse dynamics, we need a planner And for that planner, you really need to generate a kind of, to some extent, robust plans. Otherwise, relying only on the inverse dynamics cannot help you so much. It can buy you some time such that you can replan as soon as possible, but it cannot by its own generate all these behaviors.
Yeah. How about like with your inverse dynamics based approaches, if the plan is just to stand still and you lift it up, may it explode because you try to only generate forces, or
It depends. So if you control only if you control the absolute position of the center of mass, then yeah, it will go crazy if you just lift the robot.
Yeah.
But if you control the position of the center of mass with respect to the foot, then no, it's not gonna go crazy. So I think it's a technical detail, I would say, but it really depends on what you control exactly.
Yeah. Thanks a lot.
Yeah.
Okay, the next question is, it seems to me that the power supply cable acts as a stabilizer during the flat phase of the jumps. Can you comment on this and how the pose of the robot is stabilized during the very high jumps?
Okay, so actually the cable is a huge disturbance. So we are really trying to get rid of that. So we are going in the next version of the robot toward having an autonomous robot with batteries, with the communication, wireless communication, such that we don't have any kind of the wire, because it's really a huge disturbance. I don't know if it's clear here or not, but for sure it's not healthy. So this I can assure you. And the other thing is that really jumping, if you want to do one jump, I agree that it's not so you can just do simply, you can do it based on a very simple model and it's fine. However, if you want to do continuous set of jumps, it's not very easy to do. You need to have some controllers that can react very fast upon the detection of the contact or change the switch in the dynamics. So doing continuous jumping or continuous bounding is really hard with the model-based approaches. This is the thing that I experienced. And the reason is that when the robot is jumping high, because of all the uncertainty you have in the dynamics, like motor dynamics and so on, the robot doesn't jump as high as you planned. And then it will if you have a time-based controller, you really cannot handle this. So you need to have a very reactive controller that is based on a state, and you can react very fast as soon as you have contact. And even if you do MPC, which is a state-based controller, then I would say that you need to have an event-based controller, which means that you need to change your strategy as soon as you detect the contact. It's crucial. This is based on my experience. So this is something that I'm trying to looking into. And then if you want to be event-based, the thing is that your MPC loop should be super fast, because the switch between contact just happens instantaneously. So if you are not fast, it means that you're done, unless you have a very smart feedback law that can bring you to the plan. But this is a hard problem. I don't know yet how to solve with the model based, but it's a very interesting direction. However, with the learning, it's I think it's very easy to handle. You can randomize the height of the environment in the training process, and then when you do a stochastic gradient descent, you are finding kind of a solution. So because you are the policy is evaluated very fast, you have only a neural network, it can react very fast to the change in the dynamics. And I could see, I was really surprised with the performance of this controller, and I'm very happy with that. And actually, it made me very interested in learning-based algorithms, the performance I saw with this robot.
Very nice. Okay, the next question is, are the impedances kept constant for the deep RL robust jumping, or you're using some impedance adaptation scheme discussed earlier?
So here in this paper, we show, if you look at the red lines on top, it shows that the variable impedance controller is able to jump higher than fixed impedance controller. So here there is a tiny point. You should be careful about this. So it's not a simple PD control that we do around the trajectory, a time-based trajectory. The thing that you pass to the PD is the next target of the kind of, so it's not the desired position at the current time that are fed to your controller based on the trajectory planner. This is the next state that you want to end up there. So it's a bit tricky here. So this is I think is very important. But here, so we have two options. On the right, you can see variable impedance PD control. In the left, you can see fixed gain PD control. So both of them could handle very well this kind of motions. However, the variable gain gave us a bit better performance. Here, the robot could jump, for instance, 10 centimeters higher for all the different uncertainties that we had. So here we showed, we compared these two because we wanted to compare them in terms of performances, and variable impedance worked better. However, in this work, we just use the fixed impedance controller because we are not really looking here about the performance. We just wanted to show this proof of concept that if we are given a demonstration trajectory, we can find a control policy from this trajectory that is robust to different uncertainties.
Thanks a lot. Which approach do you think would be more effective for push recovery? Time adaptation, RL, or Bayesian optimization? I think Bayesian optimization, you use it just for parameter adaptation, right? So
yeah. So there also with the parameter adaptation, you can change the amount that the robot can resist against pushes. So it depends. I think if you want to do a model-based control, then I believe that you have some free parameters that you can tune. And for that, I think Bayesian optimization is a very good choice because it's very sample efficient. So you don't need to just do a grid search, or you try all the combination of these parameters. You try to smartly change these parameters to just trade off between exploration and exploitation and end up with a robust policy. So these are for model-based control. So the most of the thing actually is done by the model-based or MPC policy that you have. The thing that Bayesian optimization is doing is, I would say, 20% or something like this fine-tuning at the end. But for the RL policy, the story is different. So here, so you give a demonstration trajectory to the policy. So this is, I think, is essential because really for legged locomotion with very sparse reward space and unstable dynamic, you cannot learn this motion from scratch. So you need a demonstration. But this demonstration you can get from, I don't know, animal motion or something like that. But we have access to trajectories because we can very efficiently these days generate trajectories using trajectory optimization. And we can just generate whatever behavior we are interested in. And then we can pass this demonstration, the single demonstration, and then with an automatic framework, we can find a very robust policies. So all of them are possible solutions to me. I'm not sure yet if deep RL is the solution, or RL in general is the solution, or model-based is the solution. But these are two potential ways to have robust policies to me.
Thanks. I can ask maybe the last question. So in this work that you're showing that you're using, you're caching your trajectory optimization solution into some model. Did you have some issue with the distributional shift when you were training with when you were simulating with the TO, and then you were simulating later with the learned policy?
Yeah, this is a great question because here we are not doing simple imitation learning or behavioral cloning. What we do is that we are given a demonstration. In stage one, what we do is that we are initializing the system on the trajectory, and then we would try to just imitate the trajectory. This is the first phase, which is a function of the tracking of the demonstration, right? But the thing is that when the output policy from stage one is not going to be used. You will pass this to another training procedure, that you can start randomizing different parameters. You can randomizing initial conditions, and you want to only optimize for the reward, for the task reward. So here you are kind of doing starting from a bigger set of initial conditions. You are not only initializing on the trajectory. So you are covering a huge space of the initial conditions, and you are trying to find a policy that is valid for all this. So we really didn't see any problem with distributional shift. But while I think doing pure imitation learning or behavioral cloning would hugely suffer from this problem, because the policy will be only valid around the trajectory that you have. But here we have a policy which is not fully global, but is more global, and it has seen many different states in the training set. But in general, you cannot guarantee that you wouldn't have any distributional shift, right? So it's just by observation or by experiments that you can see that you don't observe that.